Now, how do we know there's no other path which is shorter? Well, let's just argue that directly. Let's think about an arbitrary other path and prove that it's at least as long as this one. So every SW star path P, well, what do we know about it? So remember, this is sort of the generic picture up here. So in this was some iteration. V star was already an X. The head W star was not an X. We're trying to argue that the path that we compute from S to W star is the shortest one. But what has to be true about any path from S to W star, given this picture? It goes across the frontier, right? S is on the left side, W star is on the right side. Any path between the two has to cross the frontier, at least once, maybe more, but certainly at least once, okay? So any path P from S to W star crosses the frontier at least once. And in particular, there's some initial edge, Y to Z, that it uses to cross the frontier the first time. Okay, maybe it goes back and forth, who knows? Okay, so this is just a cartoon, this blue thing is just a cartoon picture of what any path from S to W star has to look like. So, a little more precisely, so it has the form, we can think of it as comprising three pieces. Okay, so first of all, there's the part of the path that stays inside X, okay, that goes through the left side up to the frontier. Then there's the first edge that it uses that crosses the frontier. Okay, so here Y is in X, Z is not in X. And then it has to get the rest of the way to W star. Okay? So this is the key point. It's pretty simple, but really, if you agree with this point, everything else is kind of trivial. All right, so the claim is just that. First of all, we know where we stand. We know the length of our path. We have to discuss a lower bound on any other path. And the way we're doing that is by making the structural observation that every path from S to W star can be broken into three pieces of this form. Okay, a subpath lying inside X, an edge which crosses the frontier, and then maybe some extra stuff which goes from that first frontier crossing ending up at W star. Agreed? Well, let's lower bound the length. Remember, we're trying to say that our path is short, so we're trying to say that all of the paths are long. So let's lower bound each of these three sub-pieces separately. All right, so this is the easiest one. This is just one edge, okay? So the length of this is just the length of this, right? C, Y, Z. Nothing interesting there. Now what about this first part? What can we say about the length of this path from S to Y?
It's at least A of Y.
It's at least A of Y. This is where we use the inductive hypothesis. Remember, Y is inside X. It's inside what our mold has covered, what we've already conquered, and everything in there by induction is correct. Okay? So we know the shortest path to Y. Okay, it has length AY inductively. This is some path from S to Y. It can only be longer. So length at least AY by the inductive hypothesis. It's probably not very readable. Let me redo this. How about this? Who knows? But we assume that all edges are non-negative, so at least something very crude we can say is that the the length of this thing, the length of this thing cannot be negative. Okay? Uncontroversial, I hope. So, putting it all together, what are we saying? Every path from S to W star has this form, and therefore has length at least AY plus CYZ for some YZ crossing the frontier. Again, remember what that means formally. Y is an X, Z is not an X. And now finally, we are going to use the Dijkstra-Greedy criterion in our proof. We have not used it yet. We better use it. Here's where we use it. Okay. What did we do? We chose V star W star exactly to minimize this criterion. Okay. YZ is some other frontier crossing edge. It was some other candidate. It was no better than ours. Since ours was the minimum, we can replace this with A of V star plus CV star W star. By the Dijkstra-Greedy criterion, which I think I labeled star over there, hopefully. Yeah. Okay. So summing up, what did we prove? What's our path length? AV star plus C of V star W star. What's the length of any other conceivable path? Well, it's at least that. It could be worse. It's definitely not better. Therefore, our path is the shortest one. Okay? That's what we needed to prove. Question?
Why do you have to say that it is greater than or equal to A of Y? Can't you just say it is equal to D of Y?
Yeah, maybe it's using an even worse path. Who knows?
So it's not. So you don't necessarily. It's not.
I mean, I take your point. I mean, intuitively, the worst case for our proof is when this is D of Y. But notice what I'm arguing about. I'm taking any path at all from S to W star. I don't want to make any assumptions. I want to say we beat everybody. Right, so show me any candidate, any path from S to W star. So all I'm arguing is it has to get from S to Y somehow. Now, of course, the most dangerous candidates are those that use the shortest path from S to Y. So in that sense, you're totally right. But because I didn't want to assume anything, I just wrote less than or equal to. That's all I can claim. Other questions? And again, I'll show you a super slick implementation next week. Yeah.
How do you explain the last step? How do you know that A of Y plus CYZ is bigger than A of B?
That's a good question, by the definition of the algorithm. So we said, look at all the edges that cross the frontier right now. Okay, so there's like 12 such edges. Conceptually, just by brute force through the 12 of them, compute this number for each. Okay? Compute the A value for the tail plus add in the cost of that edge itself. So we get a number for each of the 12 edges, and we remember the best, and that's the one V star W star. We remember it, and that's what we use to get X. And the point is, YZ here has to be those 12 edges. Okay? Either it's also V star W star, it's one of the other 11 ones, but by brute force, we minimized exactly that sum over all 12 of those edges. So this is one of the things we beat out when we pick V star W star instead.
So we assume in the beginning that there is a direct edge. There is an edge that directly connects V star and W star.
Nope. That was just the name that we gave after the fact to the edge, which was the best. So remember, we were just looking at this cut. We didn't care. All we wanted some way of expanding X by one node. So the only thing which is important is that there's at least one edge crossing from left to right. Okay, and I'm glossing over this, but there is at least one edge by our original assumption that there's paths from S to everything else. So there's at least one edge going from left to right. There may be many. We don't care which pairs of nodes they go between. We care less. Okay?
So W star is just the name for the next node we're going to go.
W star is the name I'm giving to the node that we picked in this iteration. Okay? And YZ was some other inferior candidate. And that inferiority is exactly reflected in that inequality. Other questions?
when you cross the frontier,
Yeah.
does it function like kind of a breadth first function where you cross the frontier and then the frontier becomes smaller? You redraw the picture with more nodes and X and
Exactly.
right?
Exactly.
And then you do all those, you keep doing that until you get to your destination?
Exactly. So remember there's multiple destinations. We're computing to all destinations simultaneously. So remember, I drew x and v minus x. I give you a snapshot at a single iteration. Now, of course, this while loop iterates n minus 1 times. So there's really there's a sequence of n minus 1 pictures, just like that one on the right board. Each time there's one more node on the left and one less node on the right. Okay? But each time there's a new frontier, there's some edges crossing it. Some maybe were crossing it before, some are now crossing it but weren't crossing it before. Every time we kind of do this brute force search across the frontier to find the best one to suck one more node over to the left. Okay? So I hope that's clear. So that's just a snapshot of some generic iteration out of these n minus 1. Induction, of course, you go from justifying one of them to knowing that they all work. Yeah.
So when you do this, there's one step for calculating the path, and the other step for just picking the path that you want, the shortest. Stage and
What do you mean? So there's the base case, where you just handle the origin S, and then each iteration you basically correctly compute some other destination. Okay, so there's n minus 1 destinations, that's why there's other destinations, that's why there's n minus 1 iterations of the while loop. In each iteration of the while loop, you get one new destination correct, and it's exactly W star. W star is the one that you didn't know how to get there before, and now when you suck it in, you compute the correct way to get there. Okay, so by the end, you've got all n minus 1 of the destinations correct.